Welcome to our presentation on representing multi-robot structure through multimodal graph embedding for the selection of robot teams. This work was performed by the Human-Centered Robotics Lab at the Colorado School of Mines in collaboration with the U.S. Army Research Laboratory. Multi-robot systems can be complicated. The figure on the left shows a swarm of drones exploring an urban environment. A human may need to interact with this swarm in order to guide them to new positions or give them other commands. But multiple relationships exist within the swarm that may make it difficult for a human to conceptualize and control. There's spatial relationships, the distances between the 3D positions of each drone. There's communication relationships that define which drones have the capability to talk to each other. This can be determined by actual technical capabilities on the drone, perhaps the line of sight or distance between them. There's also organization relationships. Drones may have different roles, or a hierarchy may exist, where the human wants to control the swarm through a select drone or drones and have them pass orders to other robots. This multitude of relationships makes the swarm hard to understand, and a human needs to understand a multi-robot system in order to capably interact with it. In this presentation, we introduce an approach to make this easier by representing a multi-robot system through multimodal graph embedding. We take all of these multiple relationships that can describe a swarm and embed them into a single layer graph, a unified representation of that swarm. Then we are able to cut that into teams. This makes it easier for the human to interact with, as they can control subteams instead of a large multi-robot system. Identifying effective teams allows a multi-robot system to accomplish multiple tasks, either simultaneously or over a large area. If there are multiple buildings the swarm needs to explore, dividing them allows them to do that all at the same time. And large multi-robot systems are difficult for humans to understand. A human may not know the best way to divide a multi-robot system to accomplish multiple tasks, but we can do this by creating a unified representation. Previous work on division of multi-robot systems has been limited. Much has assigned reasons purely based on spatial relationships. Robots which are near each other get grouped into a similar team. In the figure on the right, the red robots above the obstacle have been grouped separately from the red robots below the obstacle. Other approaches allocated tasks to individuals or teams using explicit knowledge of the tasks. But if we don't have explicit knowledge of the tasks, we can't apply these. We may just know we need multiple teams ready to go to accomplish a mission without knowing details about each task that the teams might be assigned to. In this paper, we formulate robot team selection as a graph-based embedding and clustering problem, where we can model multiple relationships of robots and fuse them into a unified representation that we can then cut into effective teams. We evaluate our approach on expert-defined team formations, which have ground truth answers, large-scale simulated multi-robot systems, and teams of physical robots. And we show that it is effective in identifying robot teams and obtains superior performance over other graph-based division methods. We begin by defining each relationship within a multi-robot system as a graph. The edges define the weight that corresponds to certain relationships. For example, if the first adjacency matrix A1 describes the spatial relationships in a multi-robot system, edges may represent distance. For communication, this could be a binary factor of whether or not robots are able to communicate, or some other weight that tells us how well they are able to communicate. For something like an organization relationship, edges could indicate which robot has to report to which other robot using directed edges. And we take these multiple adjacency matrices and fuse them into that unified representation. Our approach is inspired by a social network scoring algorithm called the CATS index. In this method, the closer that two vertices are connected and the more path that exists between two vertices results in a higher similarity score. We create a new extended multimodal CATS index, which allows us to integrate multiple graphs using the paths in all graphs simultaneously. This results in a unified representation S with the same dimensions as each adjacency matrix. From this unified representation S, we want to identify a fixed length and lower dimensional representation. To do this, we take the SVD, or singular value decomposition, of S to identify the left and right eigenvectors. We concatenate each of these together to generate one representation of a fixed length for each robot in the system. We call this X. From this representation X, we are able to utilize existing clustering methods to identify teams, with the number of clusters corresponding to the number of teams necessary. In our presented results, we use a k-nearest neighbors-based approach. We first evaluated on expert-defined teams. We took these from the U.S. Army Field Manual on Infantry Tactics. These teams have known spatial relationships, the distance between agents or soldiers, a known hierarchy, there are soldiers in charge of other soldiers, known communication relationships, certain soldiers need to report things to other soldiers, and most importantly, ground truth team assignments. In the figure on the right, in the top, we see the diagram coming from the field manual, with one team in the front, a commander in the middle, and one team in the back. The bottom figure shows this represented in our multi-robot simulator, with the R method identifying these existing teams. So we compared to other graph clustering and embedding approaches, the Hope graph embedding approach, the Girvan-Newman graph clustering algorithm, and the LLE graph embedding approach. And we looked at the accuracy given these ground truth team assignments. This is given on the x-axis. As we can see, our approach achieves the highest accuracy, over 96% accurate, out of 7 defined formations. We also consider a clustering metric called the silhouette score. This allows us to later evaluate multi-robot systems where we don't have a ground truth. The silhouette score can be seen on the y-axis. Again, our approach achieves the highest silhouette score. We can also see that there exists a linear relationship between accuracy and silhouette score. Approaches that resulted in lower accuracy also resulted in lower silhouette scores. We feel this justifies this metric as an evaluation method when we don't have ground truth team assignments. So we next simulated multi-robot systems that don't have ground truth team assignments. We simulated swarms of between 10 to 50 robots and divided them into 3 to 5 teams. One example can be seen on the right in that multi-robot simulator, where we divided a swarm of 50 robots into 5 teams. Again, our approach consistently produced the highest silhouette scores, showing it identifies the most effective teams compared to other existing graph embedding methods. We also wanted to evaluate the robustness of our approach to noise. Going back to those expert-defined teams, we added simulated noise to the position of robots in the formation. The figure on the left is for a small team of about 9 agents, and the figure on the right is for large teams of 27 agents. Our approach is in red, and we compare it to the best existing graph embedding method, the Hope method. As simulated noise was added, our approach was able to maintain high silhouette scores for both size formations. The Hope graph embedding method was not able to do this, as it relies solely on spatial positions. The ability of our approach to integrate multiple modalities and not just rely on spatial positions makes it much more robust to noise, allowing it to maintain high accuracy because of its integration of communication relationships and hierarchy. Thank you for watching this presentation. In conclusion, we formulate robot team selection as a graph-based embedding and clustering problem, where we can model multiple relationships that define a multi-robot system and fuse them into a unified representation that we can then cut into effective teams. These effective teams can then accomplish tasks over a large area or just simultaneously. We show that our approach is effective in identifying robot teams on both expert-defined existing formations and large simulated swarms, obtaining superior performance over existing graph-based division methods. If you have any questions, please check out our lab website at hcr.minds.edu and feel free to contact any of the authors. Thank you.